A planner can choose a beautiful trajectory, but a robot still has to execute it through motors, gears, joints, wheels, friction, delay, and disturbance. That is the job of control. Controllers convert desired motion into commands, measure what actually happened, and correct the difference fast enough to keep the machine stable, accurate, and safe. Every feedback controller runs a simple cycle. Set a target, measure the current state, compute error, apply a command, measure again. A wheel may hit a patch of carpet, an arm may carry an unexpectedly heavy box, or wind may push a drone. Open-loop commands would drift. Feedback uses the observed result to pull behavior back toward the desired outcome. The planner answers, where should the robot go and why? The controller answers, what motor torques, wheel speeds, or joint targets should it issue right now? Planning usually works over seconds or minutes and considers alternatives. Control works over milliseconds and rejects disturbances. Blurring the roles makes systems hard to tune and debug. Their handshake is a trajectory, target, or reference behavior. PID control remains everywhere because it is understandable and effective. Proportional action pushes harder when error is large. Integral action removes steady bias, such as a wheel that consistently lags. Derivative action damps rapid changes and anticipates overshoot. Tuning matters. Too aggressive and the robot oscillates. Too timid and it lags. Simple does not mean careless. Suppose an arm must rotate its elbow to a target angle. The encoder reports actual angle many times per second. A PID loop compares that measurement to the desired trajectory, commands torque, and reduces error as gravity and load vary. The planner did not need to know every tiny disturbance. The controller absorbed them while preserving the planner's higher-level intent. Model Predictive Control, MPC, repeatedly uses a model to optimize a short sequence of future commands. It can respect joint limits, obstacle distances, tire friction, energy budgets, and smoothness constraints at the same time. Then it applies only the first command and solves again with new measurements. MPC is computationally heavier than PID, but it excels when constraints are central to safety. Humanoids and legged robots cannot control each limb independently. Whole body control coordinates many joints, balance, contacts, center of mass, and task priorities. A robot may need to keep its feet stable, hold a tray level, reach a handle, and avoid a person all at once. The controller resolves these competing requirements into physically feasible forces and motion. Physical contact is difficult because it changes the system instantly. A foot touches the ground. A gripper closes on a soft object. A wheel slips. Controllers need contact-aware estimates and fast reactions because small errors can become falls, drops, or damage. Force and torque sensing, compliant control, and conservative limits help a robot interact safely when the world refuses to behave like a perfect simulation. Learning-based control can produce fast policies for tasks that are hard to model by hand, such as agile locomotion or dexterous manipulation. Neural policies may map observations directly to actions, or learned components may augment a classical controller. The practical pattern is not replacing engineering with mystery. It is combining learned adaptation with known constraints, safety monitors, and fallback behavior. Control loops live on deadlines. Sensor delay, compute delay, network jitter, and actuator lag all mean the command may arrive after the world has changed. Too much delay can turn a stabilizing correction into an oscillation. Production robots therefore keep critical loops local, bound execution time, monitor missed deadlines, and design behavior that remains safe when performance degrades. Controllers are also a final safety boundary. They enforce torque, speed, position, and contact force limits. They can halt motion when estimates become invalid, transition to a compliant mode near people, or trigger a safe stop when a watchdog detects failure. Intelligence matters, but physical AI earns trust through predictable limits and graceful failure behavior at the actuator level. Control design begins with the plant, the motors, transmission, structure, sensors, and external loads being controlled. System identification measures how commands produce motion, including delay and uncertainty. An imperfect model can still be useful when its limits are known. A controller built on an imaginary plant will often appear stable in a demo and fail under real load. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. Control is where intention meets physics. Feedback corrects error, PID handles many everyday loops, MPC optimizes under constraints, and whole-body control coordinates complex machines. Planners choose a future. Controllers make each moment track that future despite disturbances. Without this fast, disciplined layer, even the best perception and planning would remain an unexecuted idea. Feed-forward control uses a model or reference trajectory to apply expected effort before a large error develops. Gravity compensation for an arm is a classic example. Feedback then cleans up the remaining mismatch. Together they produce faster, smoother tracking than feedback alone, especially when motion is rapid and the primary forces are predictable. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. Impedance and admittance control shape how a robot responds to contact, making it behave like a chosen spring and damper rather than a rigid machine. This is crucial for safe handoffs, assembly, and walking on uneven ground. A compliant controller can yield when it should while still maintaining enough stiffness to complete the task. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. Robots often run nested loops: current or torque control at the fastest level, velocity and position control above it, and task or trajectory control above that. Higher layers set intent, lower layers enforce it with rapid feedback. This hierarchy isolates timing-critical work and gives engineers clear places to diagnose instability, saturation, and tracking error. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. Watch for the control perspective in every physical system. Where is the reference? What is measured? How fast is correction? And what happens when a component fails? Answering those questions exposes whether an impressive robot behavior is repeatable. Stable, bounded feedback is what turns a prototype motion into dependable physical work.